really good handle on systems of equations. So you may feel like you just went back to high school with this lesson. If you don't understand something, if I'm going too fast, then please stop me and let me know. But I really feel like you're going to probably feel like you went back to high school with this lesson, which might be a good thing. I'm sure y'all could all use a little bit of a break. So hopefully that will be the case. So in chapter 8, we're dealing with a lot of systems of equations. The very first section is systems of equations that are linear, which means they're just going to be two variables in the equations, x and y, and they're all going to be to the first power. So you're going to have basically lines that either intersect or are parallel or something like that. So I feel like I said, that you're going to feel like you went back to high school here. So we're going to look at some objectives here for 8.1. We want to determine if an ordered pair is a solution to a system. We want to be able to solve a system by graphing. We want to be able to solve a system by substitution and by addition. And some books call that elimination. And then solve a few applied problems. So I think this will be an easy section for you. We do need to look at the type of solution systems that we can, type of solutions we can get for a system. If you have just one number solution, one ordered pair, that means that those two lines intersect each other at one point. So when we have two equations that we graph them and they intersect in one point, we get exactly one solution. It's called consistent because they do have a solution, and independent because they are two different lines. So any solution you get consistent. Two separate lines, though, you get independent. Now, the second case is when you have parallel lines. Parallel lines will never intersect each other. They are inconsistent because they will never touch each other. They're parallel. So in that case, you get no solution. And then if you get the same line, you get one line right on top of another line, that's an infinite number or infinitely many solutions because the lines are right on top of each other. So every point on that line is basically an intersection. So you get an infinite number of solutions along these lines. So that's dependent. And that's basically the definitions for these. So we're just going to look at some examples of each one of these types. So you've got to figure out a way to graph. I think I'm going to do this for you. I'll leave the graph there, but I'm going to work this out. Okay, so what we have here are two linear equations. And if you remember back when we were graphing, we had three methods for graphing lines. We had making a table. So to graph a line back from chapter 1, we can make a table. That's not the easy way. We can use X and Y intercepts. That's the easy way. Or we can use Y equals mx plus b. So we would use the slope intercept form. So we would have to solve for y. And sometimes we're going to have to do that, because sometimes the X and Y intercepts are not going to both be numbers that you can that are not fractional or decimals. So if I want to use the x and y intercepts, I have to do that for both lines. And you want to look at, this is ax plus by equals c, if you remember that. Ax plus the standard form. So if c divided by a and c divided by b are integers, then you can use it with no problem. So 6 divided by 1 is going to give me a whole number integer, and 6 divided by 2 is going to give me an integer. So I know I can use x and y intercepts and get integer values. So that's what I'm going to do. I'm going to say let x equal 0. So 0 plus 2y equals 6. Essentially, when you let x equal 0, the x goes away. So we divide by 2, we get y equals 3. So the y-intercept for this line is 0, 3. So we plot the point 0, 3. And then we let y equal 0 to get the x-intercept. So in that case, the y term goes away. So we get x equals 6. So 6, 0 is the x-intercept. So we plot that point. Now, like I said, this is the easy way to plot it. And if my grid was showing up here, where they cross each other is going to be obvious, but my grid's not showing up. So on the next one, I'll have a grid that shows. All right, so if we take this other equation, 2x minus y equals -8. And again, you can solve for y and get this in slope intercept form if you would rather graph that way. So the y-intercept, we're going to let x equal 0. We get negative y equals -8. So divide by -1, and we get y equals 8. So 0, 8 is the y-intercept. And then the x-intercept, we let y equal 0. So we get 2x equals -8 because the y goes away. And we get x equals -4. So -4, 0. And when you cross those two lines, they intersect at -2, 4. So these two lines are independent because they're two separate lines, and they are consistent because they cross and have an intersection point. It helps when I can spell though. So with graphing the lines, you can graph them any way you want to. You do not have to use x and y intercepts. You can solve for y, and you can use the slope and the y-intercept if that's what you prefer. Either way, it doesn't matter. All you're doing with these graphing a system is trying to find that intersection point. So let's do this one. So I think this time, oh, that is the same problem. I guess I must have worked it from scratch. That's the exact same problem. So we'll skip over to this one. Determine whether 4, -1 is a solution of the system. So if this is x and this is y, then I'm just going to plug that into each one of these equations and see if it gives me true. I'm going to go back and do another graph in just a minute, but I didn't realize I only had one. I tell you what, before I do this one, let me go back and I'm going to change this problem a little bit. Let me change this problem up a little bit. All right, so what I'm going to do here is I'm going to, this time, instead of getting the X and Y intercepts, I'm going to just show you how we can solve for Y. So I'm going to take these two equations and this time I'm going to solve for Y. So I did it with the X and Y intercepts. This time I'm going to solve for Y and get it in Y equals mx plus b form. So I'm going to subtract 2x from both sides. And that's going to give me y equals negative 2x plus 6. So the 2x's cancel on that side and you bring it to the other side, and that's one of your equations. And then I have 4x plus 2y equals 8. So I'm going to subtract 4x. So I want to get y by itself. So those cancel, and I have 2y equals negative 4x plus 8. Divide everything by 2. Now, I want you to notice something right here. Anytime you solve for y, when you're solving by graphing, it might be a good idea to just go ahead and solve for y, because if you do that and you see that you have the same slopes, if you have the same slopes, then you have parallel lines if the y-intercepts are different. So what I'm going to do is I'm going to graph these. Let me see if I can borrow a graph from somewhere. Sure, I can borrow one from somewhere if I can find one. Okay, so in this one, remember that this is the slope intercept form. So that means your slope, whoops, your slope is negative 2. So we put that over 1, and your y-intercept is 0, 6. So I want to go up to the y-intercept and plot the point 0, 6. And then I'm going to go down 2 because it's negative, but then right 1. The negative can only go with one or the other. So I'm going to go count from my y-intercept down 2 to the right 1. And I'm just going to do a couple of points. So that would be my line for that. This one has a slope of negative 2 over 1, and this one has a y-intercept of 0, 4. So I'm going to do it in a different color. So I'm going to plot the y-intercept at 0, 4, and I'm going to go down 2 to the right 1, down 2 to the right 1. And if you draw a line through it, notice those lines are parallel. They will never intersect. So we have no solution. And we have inconsistent because they never touch each other. So they're inconsistent. Now, the other thing about solving for y, and this is just advice, you don't have to do it that way. But the other thing about solving for y is if you get one of those that have infinitely many solutions, you will get the exact same equation when you solve each one for y. So you will know if you solve for y that you have the exact same equation. So it's up to you. I think it's personally with systems of equations, it's probably better to put it in slope intercept form because if you have to keep extending it to get your graphs to touch, it gives you your slope to do that. Is everybody pretty comfortable with the graphing and just finding the intersection point or finding if they have no solution because they're parallel? Or if you solved for y and you got the exact same equation, you would know that's the same line. So in that case, you would have infinitely many solutions or infinite number of solutions. Any questions on that part? Okay, so this is to determine if an ordered pair is a solution. So what you do is you just plug in your x and your y. So in this case, x is 4. So I'm going to plug in 4 for x. Y is -1. And I want to see if that equals 2. And it does. 4 plus -2 is 2. So 2 equals 2. So it works for that one, but keep in mind it has to work for both. So now I'm going to plug in a 4 here for x. And I want to, and a -1 for y. And I'm going to get 4 minus -2. And that's going to give me plus 4 plus 2 is 6, and 6 equals 6. So since that particular ordered pair works for both equations, we would have to say, yes, that is a solution. And in fact, it's the only solution for that system. So this is x. This is y. So we're going to just plug into each one. So let me just copy these down. So I'm going to put in a 1 for x. And a 2 for y. So I've got 2 minus 6. So that one checks out. I'm going to go over to the other one and plug in a 1. See if I get 4. So 5 does not equal. So it is not a solution. So the answer is no, this is not a solution. All right, the next part gives us some steps. So we talked about solving graphically. Graphically is not usually the best method to use unless there's some reason why you have to graph it. So we have some algebraic methods that work really well for us. And one of them is substitution. So here are your steps written out step by step for how you solve by substitution. So step one, solve either of the equations for one variable in terms of the other. If one of the equations is already in that form, you can skip that step. Substitute what you got for that variable into the other equation. Then you're going to solve the equation and back substitute. And then you can check your solution in both equations and make sure that it's correct. You can always check these to make sure that you did your work correctly. Okay, so step one says solve the equation for one of the variables. Well, in this case, this one already has y solved for, so we can skip step one. We already know what y is equal. So y is equal to this. So we're going to take what's in that box and in place of y here, we're going to substitute what y equals. Now the whole equation will be in terms of x and we can solve for x. Okay, so we know y equals negative x minus 1. So what we're going to do is just substitute it directly into the second equation for y. So now I'm going to do the math. So I have 4x and then minus negative 3x and then minus negative 1. So I'm going to do something different right here. Instead of doing all those minuses, I'm just going to look at that as being negative 3 times negative x is positive 3x. And then negative 3 times negative 1 is positive 3 instead of doing all those negatives. So just distribute the minus with the 3. So this gives us 7x plus 3 equals 24. Combine like terms, and now we're going to subtract 3 from both sides because we're trying to solve for x. Divide by 7 on both sides. We get x equals 3. So we're not done. We go back, and I would use the one where y is already solved for. So we got to back substitute into one of the equations. So it makes the most sense to back substitute into the one that already says y equals negative x minus 1. So I'm going to take that x equals 3, and I'm going to put it right there. So I'm substituting the 3 in place of x. So I get y equals negative 3 minus 1, y equals negative 4. That means that on the graph, those two lines intersect at 3, negative 4. So if you were to graph those two equations, they would intersect each other at that point 3, -4. So step 1 was to solve for y. It was already done. Step 2 was to substitute that into the other equation, solve for x, then back substitute x into one of the other equations, and I would substitute it into the one that already has y equal. Okay, now I want you to look at this one, and we're going to use substitution. So before we even start, which one of those equations should I solve and which variable should I solve for? I want everybody to look at those two equations and everybody tell me which equation I should solve first or second, first equation or the second equation, and which variable should I solve for? Yes, both of you are correct. All three of you are correct. The reason, because x already has a coefficient of 1. So if we could just move everything away from that x, then we would have an equation solved in terms of x. So we're going to take the second equation and solve for x. So all I would have to do, and so it's much easier to just solve for x. So now I have an equation for x in terms of y. Now I can't substitute into the one I solved, so I have to go back to the other equation. So 5x minus 4y equals 9. And this time I'm going to substitute for x. So x is this, 2y minus 3. So I'm just going to substitute for x, 2y minus 3. Now I'm going to distribute here. 10y minus 15 minus 4y. And then we just need to work that out. So 10y minus 4y. Then we need to solve for y. So I get y equals 4. And now I want to take that y that I got right here, and I want to go back and plug it in where I already solved for x. You can plug it into one of the original equations, or you can plug it into this original equation. It doesn't matter actually which one you plug it into. But since I already solved this for x, I think I'm going to plug it in right there. So 2 times 4, because y is 4. So now I know x is 5. So the ordered pair is 5, 4. That's where those two equations would cross each other if you graph them at 5 at the point 5, 4. But the algebra a lot of times is a lot easier and quicker than trying to graph. Because some equations really aren't that easy to graph either. And sometimes you get fractions for intersection points too. So if you get fractions for intersection points, you can't really pick those out by graphing. Okay, so using substitution, I have an X and a Y. Both of them have a coefficient of 1, but the Y is negative. So I still think it's easier to solve the second equation for X. So I would take X minus Y equals 3, and I would add Y to both sides. So X equals Y plus 3, or 3 plus Y, whatever way you want to write it. Now I'm going to bring this equation down. And I'm going to substitute Y plus 3 in place of X. So Y plus 3 instead of X. Distribute, and we get 3Y plus 9 plus 2Y. 3Y plus 2Y is 5Y. If we subtract 9, get negative 10. So Y equals negative 2. So I'm going to take negative 2 and put it there in place of Y. So X equals negative 2 plus 3 is 1. So that ordered pair would be 1, negative 2. Any question on the substitution part here? That's okay. Hopefully mine won't drop. To be honest, the other day yesterday I was in Monroeville teaching a class, and my internet went off, and I was on this other page over here on my PowerPoint notes, on my notes, and I didn't know. So I talked for about 5 minutes before I popped back over to the other side and realized that I had dropped connection. And so my students waited on me, but they were just sitting there and waiting on me to come back for like 5 minutes. And I was just sitting here oblivious, and I was teaching the class, and I probably taught. Thank goodness it wasn't a long lesson for them that day, because I had to go back and um, reteach. It was very awkward. I went back over there and I saw them typing. They're like, "What are we supposed to do? What should we do? I don't know." It was very awkward. So I try to pop back and make sure nothing like that's happening again. I try not to just stay on my note screen. Okay, so y'all tell me if you need some more examples with substitution, or if y'all are okay with the substitution. I'm going to do elimination or addition next, so I just need to make sure y'all are okay with what we've done so far with substitution. Is there anybody that wants some more examples? Okay. All right. So linear equations by addition. I sometimes, like I said, when I was teaching high school, most of the books call this the elimination method because you're eliminating one of the variables. So it depends on which textbook you used in high school. You may have heard it called addition, you may have heard it called elimination, but we're doing both. We're going to add to eliminate. Okay, so we want our equations to be in standard form just because it's easier to work it that way. We're going to do whatever we need to do to the equations, either multiply or divide, so that you have equal but opposite signs on either A or B. And we're going to add the two equations and eliminate one of the variables. So it's a little easier to just show you than to explain the process. So we will go to that. All right. Equation 1 here. I like to sometimes label these. So equation 1 is already in standard form. AX plus BY equals C. This one is not. So what I'm going to do is make it that way. So I'm going to move the Y term over to the left-hand side. And now that equation is in standard form. So let me erase this. I'm going to move it down a little bit. So equation 1 is 3x plus 2y equals 48. Equation 2 is now 9x minus 8y equals negative 24. Okay, so I want to multiply equation 1 by something so that I can eliminate one of the variables. Now, I can either multiply the whole equation by negative 3 and get negative 9 here, or I can multiply the whole first equation by 4 and get a negative 8 here. So it doesn't matter which one you do, but you need to do one or the other. So what I'm going to do is multiply both sides of this equation by 4. Now I'm going to rewrite equation 1. 12x plus 8y equals 192, I believe. And then I'm going to bring the second equation just straight over like it is. And now I'm going to add. I'm going to add the two equations straight up and down. So I got 12 plus 9 is 21x. These cancel out to 0 because positive 8 plus negative 8 is 0. And then here I have 8. I can't seem to do subtraction today. So 8 minus 2 is 6. I have 168. Is that right? Y'all know I get tired this time of the day. So if I divide both sides by 21, I get x equals 8. Now I've got to back substitute into one of those equations, and it doesn't matter which one. I find that students make less mistakes if they find the one that's got all the positives. If there's one with all positives, students tend to make their mistakes with negatives. So I'm going to go back and I'm going to back substitute into equation 1. So I'm going to take this x equals 8 and I'm going to back substitute it over here. So I'm going to substitute 8 right there. So now I'm just going to solve for y. So divide by 2 and you get y equals 12. So the solution for this one is ordered pair 8, 12. That's going to be their intersection point. So what did I do? I got my equations in standard form. I couldn't just add and eliminate because I didn't have equal but opposite numbers for either X or Y. So I had to figure out what I was going to multiply one of my equations by, and I multiply both sides. And I write both sides 4 times both sides of the equation to make sure I don't forget to multiply the right-hand side. I used to just do one big multiplication, and I found that sometimes I would forget to multiply the right-hand side. So I just multiply both sides by the same thing. So I'm getting an equivalent equation. It's just a multiple. All right, so what I want you to do is try this one. Both of them are already in standard form, so you don't really have to do a lot of work, but you do need to find out what to multiply one of the equations by. And sometimes you have to multiply both equations by something. But in this case, you do not. You could, but you don't have to. So if you could try this one and then just type in your answers. Okay, so I think some of y'all are getting bored with me because y'all have gone ahead and worked on this one already. Rachel, that's probably right, but I'm not sure because I haven't worked it yet. I've worked it before, but I don't remember. Get the rest, if the rest of you will work it out, see if y'all get the same thing. If I remember correctly, that's right. So hopefully y'all like this section. This is an easy section, isn't it? Maybe by the end of the section, I'll give you a little bit of a challenge. I do want to make sure everybody understands this. So I'm going to go ahead and just work through some more examples. And those answers, I believe, are correct. So let me go back to this page. So if you look at this, they call this 1, and this is equation 2. If I look at equation 2, if I multiplied equation 2 by -2, that'll give me a -4, so that when I add, I get 0. So what I'm going to do is take equation 2, and I'm going to multiply both sides by -2. So I'm going to bring equation 1 over here, and I'm going to have the same equation. I didn't have to multiply it by anything. This one's going to give me -4x. -2 times -3 is +6y equals -14. So when I add, so now I'm going to add the two equations, and this goes to 0. 4 minus 4. And then 11y equals -11. Y equals -1. Again, it doesn't matter which one we plug back into, but I think I'll pick the one with all the positives if I can. And so I'm going to plug in -1 for y. So 4x minus 5 equals 3. Add 5. So x equals 2. So I got to -1 as well. Okay, here's one where we might have to multiply both equations by something. So now we got to make a decision. I'm going to tell you that sometimes it's easier to divide. If I divided that first equation by 2 and the second equation by 3 or -3, then I would have my elimination. So I'm going to tell you that you can divide, but I'm going to I'm going to work it out where you multiply, because I don't know if everybody would understand if I did the division. But you can divide both sides by stuff. So if I divided everything by 2 up here and by 3 down here, I believe I could eliminate the x's if I made one of them negative. So you can do that. I tell you what I'm going to do. I'm going to work on, oh, that's a 9. I was already dividing in my head there. I'm going to work on the x, Because if I work on the 6 and the 9, those are kind of going to have to give me bigger numbers. What's the least common multiple for 4 and 6? Or what I'm asking is, what number will 4 and 6 both go into? You can just switch the 4 and the 6, but you're just going to get big numbers. So what I'm going to do is I'm going to use, I'm going to try to make them both equal 12. One equal 12 and one equal negative 12. So I'm going to multiply this one by 3, and I'm going to multiply this one by negative 2. Now, again, you can multiply the top one by 6 and the bottom one by negative 4 if you want to. You can also divide both equations by something, but I'm just going to multiply by 3 and negative 2. So I get negative 12x for the bottom one. So that's real interesting. Does 0 equal 12? Of course not. No. So this means this system has no solution. This would be parallel lines if you graphed them. These would be parallel lines. So when you solve one of these equations, if everything on one side cancels out to 0 and the other side gives you something besides 0, that's no solution. If everything cancels out to 0, or you have these two sides are equal, that's going to be the infinitely many solutions, or infinite number of solutions. That's where you actually have the same line. So remember, if the two sides are not equal, you get no solution. If the two sides are equal, you get infinitely many solutions. So this might be what happens to this one. I'm going to solve this one by substitution rather than by elimination, because I've done several elimination problems, and this one is already in the form. So see, when you're solving these and it doesn't tell you which way, you should pick the easiest way. So in this case, this is already solved for y, so I should just substitute. So you don't always have to use one method or another. You can pick the easy method, and substitution to me is easier this time because it's already in the form y equals, so I'll just substitute for y. So once I distribute it, I get 6 minus 4x there. So 4x minus 4x, that's 0. So I have 6 equals 6. I don't have to finish. I don't have to make them zeros. 6 does equal 6. So no matter what you plug in, what XY ordered pair you plug in, you're going to get a solution for both of those. That means that you have an infinite number of solutions, or infinitely many. Because the two sides end up equal. So your variables cancel out, but this is what tells the story. If the two sides are equal, that's what you get. Okay, so sometimes we have to use systems of equations to solve just application type problems. So what you have to do is first define your variables. So I have 2 CDs and 3 DVDs. So I'm going to let C equal CDs and D equal DVDs. And I'm going to write an equation just from what it says. Actually, I'm going to write 2 equations. So it tells me that 2 CDs and 3 DVDs equals 78. And then the second equation tells me 1 CD and 4 DVDs cost 74. So 1 CD plus 4 DVDs equals 74. Now I need to solve the system. It's already basically set up for elimination. So if I multiply the second equation by -2, both sides by -2, I'm going to get 2C plus 3D equals 78. That one's not going to change. And I'm going to get -2C minus 8D equals -148. So now I'm going to add the 2 equations, and the C's are going to cancel. So this is a D. Sorry. So divide by -5. So it looks like the DVD costs $14. Now I'm going to go back to this original second equation. So I get 1 CD plus 4 DVDs equals 74. So I'm going to plug in $14 here for D. Since it's even, I'm just going to leave off the zeros since I don't have any zeros on this side. So C plus 64 equals 74. C equals 10. So DVDs cost $14 each and CDs cost $10 each.
Ms. Rachel,
Yes.
4 times 14, that was 56.
Oh, what did I do? Yeah, that is 56. My bad. Thank you. Thank you very much. 56. Told you I couldn't add and subtract today. So that's going to give me 18. Is that right? So the CDs are 18 and the DVDs are 14. That kind of doesn't make sense, does it? Because CDs usually cost less than DVDs. But I believe that's right. Is that what y'all got? Okay. All right. I'm going to leave this next one for you to work. So see what you can do with that one. And I'm going to set this one up. First of all, can you figure out how to work this? It says Isabella paid for her $1.75 lunch with 87 coins. All of the coins were nickels and pennies. How many of each were there? Does anybody have a clue how to set this up? So what you have to do with a problem like this is you have to write an equation with, you write one equation for the number of coins, and you write another equation with the dollar amount. That's the only way to write a system for that. So I'm going to define my variable to be n equals nickels and p equals pennies. I have nickels plus pennies. I have a certain number of nickels plus a certain number of pennies, and I have a total of 87. Now, what's the dollar amount of a nickel? $0.05. What's the dollar amount of a penny? 0.01. So I have 5 cents times however many nickels I have, and then I have 1 cent for however many pennies I have, and that's going to equal to $1.75. Now, if I multiply by 100 or negative 100, actually, if I multiply by negative 100, that's going to move those decimals 2 places to the right. So it's going to get rid of the decimals. It's also going to make the p's cancel out. So I'm going to take this second equation and I'm going to multiply it by negative 100 on both sides. So remember, when I multiply by 100, you just move your decimal 2 places. So negative 5n plus 1p, or just p, equals negative 175. So now I'm going to bring this one down. So n plus, wait, that's a minus, sorry. Because I multiply by negative 100, so that should be a negative 1p minus. So I really don't need the 1, but I just wrote the 1 because I'm about to cancel them out. So now I'm going to add, and the p's are going to cancel, and I have negative 4n equals 88 negative, divide by negative 4, I get n equals 22. So I have n plus p equals 87. If I have 22 nickels, then I got to subtract from 87 to get my pennies. So I have 22 nickels and 65 pennies. And that's it. That's 8.1. We don't have to move very fast. We can do one section per day, so we're not in a big hurry. We'll be able to finish in plenty of time. We can take our time. Just go back and work that one. I know you can. Let me just give you Jason and his wife. Jason is an adult. Nathan and his wife are adults. So we want to determine the cost of one adult ticket and the cost of one child ticket. So Nathan and his wife. So we have, I'm going to help you here. So we have Jason, which is just one adult and 3 children. So A is adult, obviously, and C is children. So Jason was 1 adult and 3 children. They went to the movies for $33. Nathan and his wife are 2 adults. They took their 2 children for $38. So see if you can solve that, and just give me the answer next time we come back if you hadn't already done it. But we'll give everybody a chance to do it before we share the answer. So there's some review problems if you need practice with any of these. And that's it for today. It was an easy lesson. I hope you enjoyed having an easy lesson.